My name is Kieran Wilson. I'm a graduate research assistant at the University of Colorado Boulder, and I'm presenting a unique space simulation and test facility that our lab, the Autonomous Vehicle Systems Lab at Colorado Boulder, has developed over the last few years. So there's a lot of existing space environments, test facilities, and simulation facilities, and by and large, these are focused on flight qualification of components and materials so that we can establish a baseline knowledge of these material properties as they age in the space environment and ensure that missions will be successful. These include the Jumbo facility at SICL at the Air Force Research Laboratory in Albuquerque, the Cyrene facility at Onera, and a series of related facilities there, and even facilities like the Space Survivability Test Chamber at Utah State University. All of these facilities are typically aimed primarily at materials testing, and particularly over long durations. So the difference is our facility is aimed at exploring charged astrodynamics. So they have a lot in common with a lot of these facilities. We need similar sources of photons, electrons, ions, but instead of looking at the effects of spacecraft charging and environment exposure for materials testing, our goal is really to examine some of these new concepts in charged astrodynamics, such as electrostatic inflation, where you can use electrostatic forces to inflate large mylar structures in order to produce antennas or spacecraft wake inflation, things like that, or electrostatic debris removal, such as the electrostatic tractor concept. And a lot of this work has been done theoretically in the AVS lab in the past or in atmosphere. And one of the big problems with using atmosphere is a lot of these concepts are relying on high voltage conditions, which typically really leads to arcing and corona discharges, ionization of air, and a lot of effects that are difficult to account for. So really, a lot of these things would greatly benefit from experimental support, and particularly vacuum chamber support. So developing our own vacuum chamber facility gives us the freedom to pursue these exciting concepts and really back up the science that we're using to support these. So the goals of this facility effectively are to be able to simulate these really interesting concepts in charged astrodynamics, such as spacecraft wake manipulation, which of course would then require a streaming ion plasma, spacecraft charging explorations, for which we require things like a VUV source for stimulating photoelectric emission, high voltage power supplies. And we've also been developing new methods for sensing electrostatic potentials remotely from distances of tens of meters, which then requires a series of systems in order to measure electron and X-ray spectra. So we need retarding potential analyzers, and we also need electron guns and a lot of the systems that go to support these. So these could include 3-axis positioning systems, magnetic field control, and effectively that leads us to the Eclipse Chamber. And in 2016, we had a great opportunity. This facility, or this chamber, was donated by the Air Force Research Laboratory. It's approximately 1 meter in height and 60 centimeters in diameter. And an AFOSR DURIP grant enabled our advancement of this chamber into what it is today. So the focus of our work here is really on electrostatic actuation and touchless sensing of electrostatic potentials. So the work that we're describing today really describes the current state of the system and its capabilities. So, we received this chamber back in 2016, and it's gone through quite an evolution over the last 5 years. And its current iteration is shown in these two pictures on the right here. Currently, we have, we'll go briefly through the systems that are attached and support it. So we have an Agilent dry scroll pump, which conveniently is a really low noise system, which is important because we also have a lot of our lab space dedicated to computer work and other graduate researchers who are not involved in the chamber, and they certainly greatly appreciate a quiet scroll pump. We have a hydrocarbon-free turbo pump to go with it, and between these two, we can typically reach 1 × 6 torr in about 2 to 3 hours. We also have a new lift mechanism that we upgraded over the summer. So rather than a single column lift that it came with originally, We have 2 column lifts on either side of the chamber, which serve to stably lift it, and also enables really precise positioning of the chamber lid. It's super repeatable, and it's also remote controlled. So this has been a huge upgrade for us, and it's been really nice to have. Additionally, we have a 3-axis positioning system that works within the chamber, and somewhat uniquely, it's a cylindrical translation system. So rather than have an XYZ direction, we have a rotary stage, and then a radial stage and a vertical stage stacked on top of each other. And this really gives us the ability to maximize space inside the chamber, so we can access any part of the chamber volume, and also allows us to precisely position a probe or a source or whatever we might be interested in wherever we want to within this chamber volume. And with that, we should discuss the sources we've added and how we can actually use these. So one of our most used tools is a Kimball Physics EMG 4212D electron gun with a maximum energy of 30 kilovolts. And this gun has been phenomenal for performing a range of experiments. We use it for stimulating X-ray emission, which we can then use to determine the electrostatic potential of a target. We've used it to study charging and active charge control. And we have a range of experiments planned in the future for this too. And you'll hear more about a beam deflection experiment in a couple of presentations in this session. So one of the other big things we've been using is a phosphor screen so that we can actually visualize the electron beam and use that for accurate positioning. And the combination of these tools, along with a retarding potential analyzer to analyze beam spectra, has really enabled all sorts of really cool science, and you'll hear more about that shortly. Another great tool we've had is an ion gun. So in this case, it's an argon-based ion gun with a 5 eV to 3 keV range. And this really lets us simulate the LEO plasma environment in order to do wake experiments. So we've been developing a series of ion optics that we can add to this in order to expand the beam into something analogous to what would be experienced in a LEO plasma. This system also has a dedicated turbopump in order to differentially pump unionized argon from the flow, so that way we have a pure streaming plasma on the end. Additionally, we have a VUV lamp shown here, which we use to stimulate photoelectric emission as a peak wavelength of about 10.6 eV. And that really enables a lot of really cool experiments involving photoelectric emission for remote potential sensing, and also open up development of the broad spectrum electron gun, which is a unique capability to simulate space electron environment. So this system uses photoelectron emission from a series of differentially charged stages. So each stage has a different potential on it, but we're emitting photons from all of them. And we have the electric field inside channeled so that we can generate a broad spectrum of electron energies at once, similar to what's actually seen in space. And there will be much more detail about this in the next presentation. Additionally, we have a range of sensing capabilities. Here is an X-ray detector from Amtech and our in-house built RPA, a 3-axis Stefan-Meyer magnetometer. We have an RGA, which we use to monitor residual gases as a function of temperatures, and also our stepper motors tend to outgas somewhat as we heat them up and use them more. So this has been a great capability in order to make sure that everything's operating safely and normally. Additionally, we have a range of digital multimeters, picoammeters, cameras, encoders, and other capabilities that have all been integrated into this facility in order to give us a really adaptable capability set. So, with that, we've used this a lot in the past in order to develop 2 novel means of touchlessly sensing spacecraft potentials using X-ray and electron spectra. And we've also developed a novel electron gun concept for space simulation, which we're now applying to a whole bunch of new problems. And we've also been able to use this facility already to validate numerical models for flexible materials affected by electrostatic forces. So as mylar deforms under electrostatic interactions with the space environment, we can now simulate that effectively. Additionally, we have a magnetic coil system in development, which we hope to add in Q1 of this coming year. We have high precision encoders to our translation stages, which will also enable a wide range of future experiments. Paper offers more detail of these systems and a whole bunch more, so if you have any questions, feel free to reach out. The next couple of presentations will dig deeper into our capabilities and what we've actually done with them. Thank you.